Grounding is essential for electrical safety. It provides a safe path for fault currents to flow back to the source, which prevents electrical shocks and equipment damage. The National Electrical Code, or NEC, specifies grounding requirements based on system voltage and environmental conditions. In a sand mine, achieving low grounding resistance can be challenging due to the poor conductivity of the soil. However, an aggressive approach to grounding has proven effective in meeting revised corporate standards. Driving threaded ground rods into the soil and connecting them in series is a common method to lower grounding resistance. As the dirt settles, the resistance typically decreases. Adding an additional ground rod, if necessary, can further reduce resistance to below 5 ohms. Supplemental external grounding wiring was found to be a more practical solution in repairing existing wiring that had deteriorated over time. Adding external ground connections enhances the continuity of the grounding path. Maintaining a low grounding resistance is crucial for several reasons. Firstly, reduced fault current is achieved. Low resistance limits fault current, ensuring that protective devices, such as circuit breakers or fuses, can operate effectively. Secondly, it enhances safety. Low fault currents minimize the risk of electrical shocks and fires. Thirdly, equipment protection is improved. Proper grounding helps protect equipment from damage by providing a safe path for fault currents. Through the installation of threaded ground rods and supplemental grounding wiring, it is ensured that fault currents can be effectively cleared, protecting personnel and equipment. This approach aligns with the importance of meeting revised corporate standards and NEC requirements. Most of the equipment is 460 volts. It is important to understand the code requirements for grounding resistance. The National Electrical Code specifies maximum resistance values for grounding electrodes. The resistance between the grounding electrode and the earth should not exceed 25 ohms. In situations where a single grounding electrode does not meet the 25 ohms requirement, an additional electrode is required. These electrodes must be placed at least 6 feet apart. Lowering grounding resistance is crucial for safety and proper operation of electrical systems. The lower the resistance, the more effectively fault currents can be directed back to the source, tripping circuit breakers and minimizing the risk of electrical shock. Several methods can be used to lower grounding resistance. One common method is to drive ground rods deeper into the earth. The deeper the rod, the more contact it has with the soil, which reduces resistance. Another method is to use multiple ground rods connected in parallel. Connecting multiple rods effectively increases the surface area in contact with the earth, lowering the overall resistance. Soil conductivity can be improved by treating the soil around the ground rod with ground enhancement materials. These materials typically contain minerals that help to retain moisture and improve conductivity. Regular testing of grounding systems is essential to ensure that they remain effective. Ground resistance testers are used to measure the resistance between the grounding electrode and the earth. Measurement should be taken periodically, especially after significant changes in soil conditions, such as after heavy rainfall or prolonged dry periods. When installing ground rods, proper spacing is crucial. The NEC requires a minimum of 6 feet between ground rods to avoid overlapping spheres of influence. Overlapping spheres can reduce the effectiveness of each rod. The size and type of grounding conductor also play a critical role in grounding system performance. Grounding conductors must be sized appropriately to handle the maximum fault current that could flow through them. Copper conductors are commonly used due to their excellent conductivity and corrosion resistance. The grounding electrode conductor connects the grounding electrode to the equipment grounding busbar in the electrical panel. This conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. Grounding systems should be visually inspected regularly for signs of damage or corrosion. Check the connections to ensure they are tight and free from corrosion. Replace any damaged or corroded components immediately. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and underground metallic water pipes. Ground plates provide a large surface area in contact with the earth, which can be effective in reducing resistance. Underground metallic water pipes can be used as grounding electrodes if they meet certain requirements outlined in the NEC. The NEC specifies different grounding requirements for different types of electrical systems. For example, the grounding requirements for separately derived systems, such as generators and transformers, are different from those for service entrance equipment. Understanding these specific requirements is essential for ensuring proper grounding. In industrial settings, it is common to use a grounding grid, which consists of a network of interconnected grounding conductors buried beneath the surface. Grounding grids provide a low impedance path for fault currents, which is particularly important in facilities with sensitive electronic equipment. Grounding and bonding are two distinct but related concepts. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting non-current carrying metal parts of electrical equipment together to create a continuous electrical path. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. The NEC requires that all metal enclosures containing electrical conductors or equipment be bonded together. This includes metal conduits, junction boxes, and equipment cabinets. Bonding jumpers are used to connect these enclosures together, creating a continuous electrical path. Effective grounding and bonding are essential for protecting both people and equipment from electrical hazards. By following the requirements of the NEC and implementing best practices for grounding and bonding, it is possible to create a safe and reliable electrical system. Remember that the effectiveness of a grounding system can be affected by various factors, including soil type, moisture content, and temperature. Regular testing and maintenance are essential for ensuring that the grounding system continues to provide adequate protection over time. When working with electrical equipment, always follow safe work practices and use appropriate personal protective equipment, such as insulated gloves and safety glasses. Never work on energized equipment unless you are properly trained and qualified to do so. Grounding is a critical aspect of electrical safety, and it is essential to understand the principles and practices involved in designing, installing, and maintaining effective grounding systems. By following the guidelines and recommendations outlined in the NEC, you can help to ensure the safety of yourself and others who work with or around electrical equipment. In addition to the NEC, other standards and guidelines may apply to grounding systems in certain situations. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards on grounding for industrial and commercial power systems. These standards provide more detailed guidance on specific aspects of grounding, such as grounding electrode design and grounding system testing. It is important to stay up to date on the latest standards and guidelines related to grounding in order to ensure that your grounding systems are in compliance and provide the best possible protection. Grounding is not a one-size-fits-all solution, and the specific requirements for a grounding system will vary depending on the application and the environment. A qualified electrical engineer should be consulted to design and specify grounding systems for complex or critical applications. Grounding is a fundamental aspect of electrical safety that should not be overlooked. By understanding the principles of grounding and following the requirements of the NEC and other applicable standards, it is possible to create safe and reliable electrical systems that protect people and equipment from electrical hazards. Grounding is achieved by providing a low impedance path from electrical equipment to earth. This path allows fault currents to flow safely back to the source, tripping circuit breakers or fuses and preventing electrical shock. Effective grounding requires careful design, installation, and maintenance. The NEC provides detailed requirements for grounding systems, including the types of grounding electrodes that can be used, the size of grounding conductors, and the methods for connecting grounding conductors to equipment. Grounding electrodes are typically made of copper or galvanized steel and are buried in the earth. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The size of the grounding conductor depends on the size of the service entrance conductors. The NEC provides tables that specify the minimum size of grounding conductors for different service sizes. Grounding conductors must be securely connected to equipment using approved connectors. Connections must be tight and corrosion resistant. Grounding systems should be tested regularly to ensure that they are functioning properly. Ground resistance testers are used to measure the resistance between the grounding electrode and the earth. The resistance should be as low as possible, but should not exceed 25 ohms. If the resistance is too high, additional grounding electrodes may be required. Grounding is an essential part of electrical safety, and it is important to understand the principles and practices involved in designing, installing, and maintaining effective grounding systems. By following the requirements of the NEC and implementing best practices for grounding, it is possible to create safe and reliable electrical systems that protect people and equipment from electrical hazards. Regular inspections and maintenance are crucial for ensuring the continued effectiveness of grounding systems. Check for signs of corrosion, damage, or loose connections. Repair or replace any damaged components immediately. Keep the area around grounding electrodes clear of debris and vegetation. This will help to prevent corrosion and ensure that the electrodes are properly grounded. Grounding is a complex topic, and it is important to consult with a qualified electrical professional if you have any questions or concerns. A qualified professional can help you to design, install, and maintain a grounding system that meets your specific needs and requirements. Grounding is a critical component of electrical safety, and it should never be taken lightly. By taking the time to understand the principles of grounding and following best practices for grounding, you can help to protect yourself, your family, and your property from electrical hazards. Grounding is particularly important in industrial settings, where there is a greater risk of electrical shock due to the presence of heavy machinery and equipment. In industrial facilities, grounding systems should be designed to provide a low impedance path for fault currents, which will help to trip circuit breakers quickly and prevent electrical shock. Grounding grids are often used in industrial facilities to provide a comprehensive grounding system. Grounding grids consist of a network of interconnected grounding conductors that are buried beneath the surface of the facility. These grids provide a low impedance path for fault currents, which helps to protect people and equipment from electrical hazards. Grounding is not just about protecting people from electrical shock. It is also about protecting equipment from damage. Electrical surges can damage sensitive electronic equipment, and grounding provides a path for these surges to flow safely to ground. Surge protective devices, or SPDs, are often used in conjunction with grounding systems to provide additional protection against electrical surges. SPD are designed to divert surge currents to ground, protecting equipment from damage. Grounding is a fundamental aspect of electrical safety, and it is essential to understand the principles and practices involved in designing, installing, and maintaining effective grounding systems. By following the requirements of the NEC and implementing best practices for grounding, it is possible to create safe and reliable electrical systems that protect people and equipment from electrical hazards. It is also important to remember that grounding is not a substitute for other safety measures, such as wearing appropriate personal protective equipment and following safe work practices. Grounding is just one component of a comprehensive electrical safety program. A complete electrical safety program should also include training, inspections, and maintenance. By implementing a comprehensive electrical safety program, you can help to create a safe working environment for yourself and your colleagues. Grounding plays a critical role in ensuring the safety and reliability of electrical systems.